My name is Doug Sartori. I am the principal consultant at Parallel 42 Systems, and tonight we are going to walk through a practical introduction to SQL. Before we get into it, I just want to suggest that if you have questions, please hold them till the end or drop them in the chat. There is a lot of material for us to cover tonight. I want to make sure that we get through it all. We're going to start by talking about some of the fundamentals that you need to understand to be able to use SQL effectively. And a little bit later, there is a demo and you can interact if you like. There's some tools that you can use in a browser to work along with us. And when we get to that point, I'll give you the URL and you can have at it. So before we can talk about SQL, we need to talk about relational databases. Relational databases are the home where SQL lives. SQL is the programming language that we use to talk to relational databases. Relational databases are a way of logically storing data to minimize error and maximize storage space. They were developed back in 1970, which officially makes it an old technology because it's older than me. Relational databases store data in tables, okay? Uniquely named tables of columns and rows. So it's useful to think about an Excel spreadsheet when you think about relational database tables. Spreadsheet and tables look a lot alike. They both have rows and columns. But the differences, I think, can help illuminate what is important and useful about relational databases. In a spreadsheet, you can put any information that you want anywhere in the sheet. In a relational database table, the number of columns is defined ahead of time. Each column has its own unique name, and each column has a specific type of data that is allowed to be put into that column. So if you think about the different data types, you should be thinking about things like dates, numbers of different kinds, integers or decimals. Character values can also be stored in columns. So each column has a specific type of data, and that is the only kind of information that can be stored there. And that is important because it allows us to have very predictable data in our databases, and it reduces errors. If you can't put bad data into a column, then you know that your database won't have bad data. And the rows in a relational database table are the instances of data. So we have named columns. Picture again that Excel spreadsheet with a set of column names across the top, and each row has a unique piece of information in it for each column. The relational model was proposed in 1970 by a person named E.F. Codd. And over the next few years, he elaborated in a series of papers what are called normalization rules. Normalization is a complicated set of principles of database design, but there are a couple of rules of thumb that if you understand, you will be well on your way to being able to use them. Tables store data about one kind of thing. So each table should be a logical entity that is alone by itself. If you have a table of students, that the information in that table should not include, for example, information about the classes that the student is in, or information about the people who teach those classes. Information about those things should be stored in their own tables. And these principles of normalization were designed to solve common problems that people working with data encountered prior to the development of the relational model. So we talked a little bit a moment ago about keeping data related to one thing in one table, and we use keys to relate those tables to each other. Okay. One other thing that I want to mention is that implementations of relational database are really widespread. It's one of the most common ways to store data out there. You'll you'll think of products from vendors like Microsoft with SQL Server. There are open source products like MySQL, PostgreSQL, Oracle. We're not going to talk much tonight about specific relational database engines. That opens a whole can of worms of complexity. So that's one of the reasons why, instead of dealing with a database engine in my demonstration tonight, we're going to use a simple browser tool that simulates one. Okay, so I'm going to show you a couple of examples of database tables and the relationships between them. This example shows a one-to-many relationship between teachers and the classes that they teach. So in the teacher table, we see a list there of column names. This is a pretty common way to represent database tables in design. There is a unique ID for each teacher. There is a name, office location, phone, email, et cetera, et cetera. And then we have a table of classes that an individual teacher might teach. Those classes also have an ID, the class ID. There is a space in the table for the course code, what day of week that course is taught, the time it starts, the time it ends. And then if you see that second bolded column in the classes table is the teacher ID. Okay. Now, again, this is a one-to-many relationship. The teacher ID, you see that little one in the diagram next to the line that connects the teacher ID and the two tables. In the teachers table, it's a 1. And the symbol in the class that is attached to the classes table indicates that that is many. And what that means is that for every one teacher ID, there can be many teacher IDs in the classes table, because of course, one teacher can teach many classes. So that's the most common type of relationship between tables. Typically, there is a table that has some piece of master data like a teacher or a student, and then a table with some detailed data that connects to it. There are other kinds of relationships, one-to-one relationships, which you don't see very often in practice, but in some circumstances, they can be useful. For example, when you're relating data across two different databases, or when you're working around some technical limit in a specific database management system. You also will see many-to-many relationships when you are modeling something that's a little bit more complex, and you have two tables of data, each of which can have many instances of a specific identifier. What I want you to take away from this slide, though, is that tables use IDs to connect to one another. When we have a key, which is another name for ID. When we have a key that identifies the row, that's called a primary key. So the teacher ID in the teachers table would be a primary key. In the classes table, the primary key would be the class ID, and the teacher ID that is present in the classes table is a foreign key. And the foreign key is what you use to connect to another table in which that key is the primary key. Okay, I know this is a lot of information. We're kind of drinking from the fire hose here. But what I'm trying to do is give you the essential things you need to know about databases so that we can write some effective queries. Okay, here is another example, a little bit more complicated. Now we have 3 tables related to one another. So to identify the cost of activities for one particular student, you would need to join all 3 tables together. It might seem like this is a cumbersome way to do things, but remember, these relationships are defined this way to avoid problems. When you have data that is all mushed together in one table, as you often see in spreadsheets, where you run into problems when that data gets to be at a bit of a larger scale, you run into problems where it's very difficult to add data or remove data without running into problems. For example, if we had, going back to that previous slide, if we had a database that was a flat spreadsheet that contained teachers and the classes that they taught, If a teacher went on sabbatical and you removed the last class that they taught, then the teacher would also be gone from the database. So these are the reasons why we have this structure, and it's important to understand it if you want to be able to query databases. So let's take a look in a little bit more detail at this specific example. Here we have a students table with a list of students and an ID. Then we have a participants table. Okay, and this table looks like it is keeping track of which students are participating in a particular activity. So we have an ID, but it looks like this table, and it's mostly, I think, for the purpose of being simple and being a simple representation. The participants table doesn't have a primary key. It doesn't have a key that is unique for every row. So we see there is repeated data in the ID column, and there is repeated data in the activity column. We have multiple instances of swimming, multiple instances of student 84. Then in the activities table, we have a list of activities. And in this case, the key, the primary key, is not a number. It's actually the name of the activity. And you can see in this little table that the activity is unique. There is only one instance of each activity in that table. So the primary key in the activities table is activity. The primary key in the student table is ID. And the participants table consists only of IDs. It doesn't have, or only of foreign keys rather, excuse me. It doesn't have any unique data of its own. So this is an example of a many-to-many relationship. If you want to find out how much John Smith is spending on activities, you have to join all three tables. Okay, in order to do that, we need to now start talking about the query language that we use to actually talk to databases. SQL stands for Structured Query Language. It's a domain-specific language. So what that means is that SQL is not a general-purpose programming language. You can do anything you want with SQL. It is Turing complete. You could theoretically do any task with SQL, but it is focused on the task of querying databases, and that makes it a domain-specific language. Typically, domain-specific languages are have a little bit simpler syntax and have tooling that is aimed at solving one specific set of problems, and that's what SQL is. It's also an imperative language. So for those of you who have some experience with programming, most programming languages are procedural. And what that means is that you tell the computer each step that you want it to do. 10 print hello, 20 go to 10. Every line of that program is a detailed instruction for what you want the computer to do. An imperative language is a little bit more abstract. You're telling the computer what you want, not how to do it. So SQL is about describing the data set that you want the computer to give back to you. The relational database engine will then take your query and figure out the best way to get that data to you. And you could have two very similar queries. They may look very similar, but under the hood, the relational database engine will be using completely different tools to access that data. All of that is abstracted away from you. All you have to worry about is telling the computer what you want. SQL is also old. It was developed at IBM back in the 70s. It has been standardized for many years, but each vendor has its own flavor of SQL. Typically, if you stick to the ANSI standard, the American National Standard Institute standards, typically if you stick to those standards, you'll be able to write queries that almost any database management system will understand. Then each management system has its own flavor of SQL, which will bring in some convenience features and tools that are related to their specific database. So this is the way that you talk to relational databases. SQL is a language that has a number of different components. Okay, we write queries to ask the database engine to give us back a set of information. We do that with the select statement. And there are also a number of other components. Data definition language is code that deals with creating and updating the actual structure of a database. We're not going to get too deep into DDL today, but you will get to see what it looks like when we get to the demo, because there is a bit of DDL that we need to use to set up our database. Data manipulation language are tools for storing, modifying, retrieving, and deleting data in databases. Data control language is mostly concerned with rights, permissions, and system control. And transaction control language manages transactions. So this is a feature of relational databases we haven't touched on tonight, mostly because it's an advanced topic. So I'll just give you in a nutshell, transactions are a way of bundling statements together to make sure that the database remains consistent the way you want it to. A good example of a transaction would actually be a financial transaction, say a bank deposit or a transfer. Every accounting transaction at a bank has a credit and a corresponding debit. We credit one account and we debit the other account. And we definitely don't want half of that transaction to happen and the other half not to happen. So SQL includes transaction control so that we can bundle statements together. And if at any point in our query, if at any point it fails, the whole thing gets rolled back. So you never end up with a debit that doesn't have a matching credit or a credit that doesn't have a matching debit. That is a high level view of the parts of SQL. And for the rest of tonight, we are going to narrowly focus only on that first bullet point, the select statement, which may sound like it's a really trivial thing, but if you take a look at the syntax diagram for the select statement, you'll see that it's pretty complicated. I'm not expecting you to make a whole lot of this right now, except to point out that this one command has a ton of complexity. In my professional work, it's not unheard of for me to spend a whole day or more writing and testing one single select statement. So it's definitely something that is really big. And this is the place where you should start in your learning journey with databases and SQL. So the good news is that a basic select statement, which is what we're learning about tonight, is pretty simple and you can do a lot with it, but I want you to understand there's a lot of power and complexity there, a lot of tools that you can use to get exactly the information that you want. So I just want you to know that there's a lot of power there. And as you go forward working with SQL, if there's something that you want to do and you're not sure how to do it, you should look at your vendor's documentation and you should start with the documentation for the select statement, because it will contain many examples and lots of details about all the different things that you can do with it. So we query data with the select statement, and there is a structure to a select statement. We identify the specific columns of information we want in the select clause. Then we specify the source of data that we want to query with the from clause. We filter data with the where clause, and we connect data with join syntax. Okay, those are the four basic parts of an SQL query that you need to be able to do anything very effective. This is a good time for us to take a look at our sample database. So I've got a sample set of DDL that you can use. And the URL is right there, github.com/dsartori/SQL intro. And what I'm going to do now is I'm going to shift my screen share over to my browser so that you can watch me as I do this, this piece, and hopefully follow along on your own. Okay. Okay, I've got all you lovely people at the bottom of the screen there. Just move you out of the way. Okay, so if you've navigated to that URL in your browser, you should see something that looks like this, and it is about 70 lines of code. And what this code will do when we copy it, and then we go over to a website called db-fiddle.com. And if you navigate to db-fiddle and you paste that schema in the schema window, okay, so this is the DDL that is going to create a simple database for us. Sorry, I'm missing something. There we go. And now I've got my my schema is loaded and it's ready to accept queries right over here. So let's take a look again at our sample database. And we'll look at the diagram. Okay, move you guys out of the way there. So this sample database is a set of tables that support the inventory for a toy store. So we have one table called toy info that has information about the toys that we have in inventory. So you can see there is a primary key, the toy ID. Then there is a description of the toy, the color of the toy, the cost, and the weight. You can see that this particular database diagram identifies not only the name of the column, but the data type. If you remember, we talked about data types way back at the beginning. So a varchar 30, which is what that first toy column is, means character varying up to 30. So we can have any text we want up to 30 characters long. Then the other unique ones in here are the integer type, which stores any integer number between a certain range. The cost is a decimal, as is the weight. Decimal, that data type specifies the precision and the length of that particular decimal number. So in this case, we have a decimal number that is 5 total digits long, with 2 digits after the decimal place. The store inventory table has foreign keys for the toy info table, as well as the store info table, which we'll get to in a moment, and then an integer value that stores the quantity in inventory. And finally, the store info table has an ID of a unique identifier, it has the address of the store, it identifies the phone number of the store and the name of the manager. So pretty simple, something that we can work with and write some basic queries. The most basic query that we can write is right there on the screen. I encourage you to type that in and give it a shot. The asterisk is a wildcard character. So what that allows us to do is get all of the columns from a table. So this is a pretty common construction. Select star from toy info is going to dump out to the output, whether that is the output on the screen or wherever you're sending your query output. It is going to send the entire contents of the toy info table to the output. Pretty simple. So I encourage you to give it a try and see what that looks like. I'm just going to go ahead and do that now. So we'll switch over to our other window here. And okay. And we can run it. And there is our output here at the bottom of the screen. And you can see in the results panel, it is showing us the entire contents of that toy info table. Okay. Pretty simple stuff. Now, if you want to get a little bit fancier, you can specify which columns that you want to display in the result set by providing a comma-separated list in the select statement. So for example, select toy, comma, color from toy info is going to return the same dump of the entire table that we saw before, except that we're only going to see the toy and the color columns. And that's valuable because you often have tables that are much longer in terms of the number of columns than you see in our sample database. And you very often only want to get a subset. And especially when you're joining tables and you're looking at columns from multiple tables, it would be extremely cumbersome to look at all of them at once. So that's the way that you limit the number of columns, but we're still getting all the rows in our result set. So the next step is for us to add a clause to that query to limit the number of rows that we see. And the way that we do that is by using the where clause. So the where clause allows us to specify a column and a condition that that column has to meet in order for that entire row to fit into the result set. So we don't necessarily need to limit the output based on our condition. In fact, the condition doesn't even need to be in the output that we've selected. They're independent. The column that you are specifying, you have to create a Boolean condition, a logical condition that can boil down to true or false. So you do that by identifying the column name, adding an operator to specify the logical condition. And you can see in these examples what those kind of operators look like. We use the less than indicator to identify an operation that we want to see only values less than the one we specify. We use the equal sign operator to indicate that we only want values that equal that number. And then we specify the value. So that little construction there, where cost is less than $2, is a pretty simple example of a where clause. You can have multiple where clauses and string them together with another set of Boolean commands like and or. And you can even use brackets to group sections of the where clause. So this is something that you should practice, because subtle logical errors in Boolean conditions are one of the more common problems that you'll encounter when you're debugging a query. Okay, so let's switch back to our demo and we will try a couple of these. We'll try a couple of examples. Okay, so let's try, that first one. Okay, you can see our result set is a lot smaller now because we are only seeing the toys who match this condition, where cost is less than $2. We can now try a compound where clause. For whatever reason, we want to see anything that is less than $2. Oh, that's not going to work. How about we do this? We'll change that up. So now what I've done is I've adjusted this query. So for whatever reason, we want to see the information from the toy info table where the cost is greater than $2 or where the cost is equal to $1.50. Oh, sorry, press the wrong button. I think they've changed the interface because I keep wanting to go to the wrong spot. There we go. And if you look over here in the results specifically at the cost column, you'll see that we have a whole bunch of toys that cost more than $2. And there is this one specific row where the cost is equal to $1.50. So we have successfully created a where clause that has multiple conditions in it. The other thing that we can do, just to give you another example. So something to note there, when we're writing SQL and we are searching for character data in a column, we do have to identify that character data by quoting it so that the SQL interpreter knows that that is a specific string of character data and not a column name or something else. And now you can see that we're only looking at yellow toys that cost over $2. So there is an example of a where clause that is combining two conditions. So a logical OR allows us to have two separate conditions that can be met in order to for that row to qualify and be in the output. And the logical AND allows us to combine conditions so that both have to be met in order for that row to appear in the output. Okay, again, this is something that I strongly suggest that you practice. There's a lot of stuff here, but hopefully that will give you enough information to get started. Okay, heading back to our slides now. Okay, and the last thing that we need to talk about is how to join tables, adding more tables to our query so that we can get data from multiple tables. The relational model, again, requires us to split data into multiple tables to eliminate repetition and to make adding and removing data more reliable. But it also means the data that we want to see is often spread across multiple tables. So the price that we pay for more efficient and more accurate data storage is a little bit more work, a little bit of a cumbersome process in order to get exactly the data that we want. The join clause of the select statement is what allows us to query multiple tables at once. And there are a number of different ways to join tables. So I'm going to put the next slide up. This is a little bit of information overload, I'm sure. What I want you to take from this is that when you consider the set of data that you want to get back, you have to make the right choice in terms of how you are going to join those two tables to get the right set of data. So you can see this is a pretty classic diagram. You'll see it quite a lot. The different Venn diagrams, A and B, are showing they represent the content of different tables. And so the overlapping area between A and B is where we have data that lines up. If you want to get only the information that is contained in both tables, you use an inner join, which is the center of our diagram here, that center example. That's the most common type of join and the most useful type of join. I would say most of the time that is what you want. The next most common is the left and right join. Sometimes you're going to want, like, to go back to our example of students and activities. You might want to generate a list of all students, whether they are participating in an activity or not. Or you may want to generate a list of all activities, whether any students signed up for it or not. And if you want to do that, then you're going to need to use a left or a right join. But otherwise, if all you want is the intersecting data, then you want to use an inner join. The other join types are far less common. You can go a long time without ever having to use them, but just know that they're there, and know that they are available to you. One of the things that you will often see as a pitfall is when you construct a join and you end up with more data than you expected or repeating data in your output, that means you probably have to go back and take a look at your join syntax and think about where whether you're doing the right thing in terms of your query. Okay, so we're going to focus on the inner join. This is definitely the most common way to join tables. It gets, as I said a moment ago, only rows from the tables that match the condition from both tables. And this is almost always what you want. It's a good idea to experiment with different join types to get a feel for when they might be useful. But we've got a sample query there, and I encourage you to take a shot at it and type it in. I'm going to, and we'll take a look at the results together. Okay. Got to look over at my notes here. So we are going to specify the columns that we want. And you may notice, whoops, that there is a letter and a dot before the column names. That doesn't appear in our data definition language over here on the left. And I'll explain that in just a moment. Okay, so I want to know the store ID, the name of the toy, and how much inventory that store has. So we pick a table and we make that our first table in the from clause. Okay, there is our alias, and that's what these prefixes on the column names are. They are aliases because it would be really cumbersome visually, and it would take a long time to type if we typed out the full table name to prefix every column in our select list. So SQL has the convenience feature that you can alias a table and identify it with just a single letter or an abbreviation. And that's what that is. So we are identifying store inventory as I. Okay. And now we're going to join another table. Okay. We're going to inner join toy info and alias it to T, just like we have in our select list. And then we have to tell SQL how we want those two tables to be joined, what columns we want to use, and what logical operator we want to use. So toy ID in inventory needs to be equal to toy ID in the toy table. And you can use any logical operator that you can use in a where clause. You could use that here in a join as well, because this is actually just a little bit of syntax sugar to make joining tables easier. It's actually what it is a specialized kind of where clause. So that means that you can actually have multiple conditions and connect them with Boolean commands like and or, and you can have any logical condition that you want. Most of the time, what we want is to make sure that the key in each table is equal. Okay, now we are not done because we have to add a third table here. Okay, and that is store info S on store ID equals I store ID. So if you go back and think about the diagram that I showed you a while ago, these are the keys that connect these tables. So now when we execute this, what we should see is the store ID, the toy, and the inventory. So we've taken data from 3 different tables, and we are getting only the data that we want. And we are using the join facility in SQL to connect those tables together. So there's a few things that I wanted to point out here. So one of the problems with this sample database, or maybe I prefer to think of it as an opportunity for us to learn together. One of the problems with this database is that the toy table actually it has a little bit of an issue in that the toy table breaks some normalization rules. So we have repeating data in the toy table. Yes, every instance, every row has its own unique ID, but we have multiple instances of the same toy name in different colors. And this is something I don't want to dig too deep into it, but it's probably helpful if I add the color column to the query and execute it, and it'll be a little easier to see the problems that can happen. Okay, so in this row, we have store ID 1 has 34 yellow frisbees. Okay, so far so good. Store ID 3 has 12 yellow frisbees. But here we have a row, oh, okay, store ID 1 again, and 5 more yellow frisbees. So this is a problem. And part of this problem is emerging because we are not identifying toys uniquely and then have with a separate table of colors, so that we could, for example, find out exactly how many frisbees we have in a store without having to, do math on the result set. We also have a problem in that we have not enforced uniqueness in the inventory table, which we probably should, because we don't want to end up with multiple versions of the truth, which is what we've got here. We have 2 inventory amounts for yellow frisbees in our in store 1. So what that tells you when you see stuff like that, that tells you that there are some challenges with the design of the database. Now we can do things with our queries. We can do things with queries to solve some of those problems, or at least to work around them when we're querying data. That's a little bit out of scope for today's discussion, but I wanted to just point that out. These are areas where you could dig a little bit deeper and maybe take the next step in your learning journey by trying to improve the tables and data in this sample database to work through some of those problems. So last slide. Okay, we're going to go back to our slides. Last slide here. And what I want to do is just share a few tips about effective database querying. So you need to understand your data and its structure. It's really hard to write queries effectively if you don't understand what the tables are intended to store, how they relate to each other, and everything else about them. You need to know your data and how it's structured. It's really important. So it's good to be able to investigate the database. How that usually looks for me, the first thing I'll ask when I'm working with an unfamiliar database is, how do you have a database diagram? Do you have any documentation on this database? Is there anything that I can look at? And sometimes the answer is no. In which case it's time to start querying. And that's where those wildcard select statements come in handy. You can take a survey of an entire table of data, then survey the next table and start to understand how they relate to each other. It's always a good idea to visualize your result set before you start writing your query. You want to know what you want to see so that you know what success looks like. And then you need to test and evaluate your results. You should not write a query no more than you should write any other kind of computer program and assume that you got it right the first time. You need to test it. You need to evaluate the results. You need to compare those results that you're getting in your output against maybe other queries or a survey of the entire contents of the table. It's really important to debug your queries, because when you write a bunch of queries and incorporate them into a report or a larger piece of software, it can get really tough to suss out exactly where the trouble is if you didn't do that basic work when you got started. So that is pretty much everything I had for you tonight on the basics of querying relational databases.